Wow.
Okay. Welcome to my second part of the talk on introduction to higher form symmetries. So it's going to be a continuation of the previous talk, and I'll be going pretty fast through the recap. So I apologize for those who have not heard my first talk. Yeah, but previously I received feedback that I didn't include enough examples. So this time it's all going to be examples to help us better understand the result we got previous time. So my thesis supervisor is Tutor. Okay, so we'll do a quick recap and then we'll look at one form symmetries in 1 plus 1 dimension, 2 plus 1, and 3 plus 1. And if we really have time, we'll do Maxwell theory, but I believe we don't. Okay. Anyway, just a quick reminder of why we care about higher form symmetries. Well, this leads to topological operators, an example of which is Wilson loops. And these Wilson loops appear in a variety of contexts, including in condensed matter, H theories, and also string theory. Now, previously, the last time we started with Noether's theorem, we mentioned that Noether's theorem talks about symmetries. If you have a field that varies in a particular way, governed by the form of the variation as well as the infinitesimal parameter, then if it's a symmetry, your action should be invariant to first order. So if you have an extremized field to begin with, then you can impose the equations of motion and we end up with a continuity equation. And this object, we call it the conserved current. Now, for the purposes of generalization to higher form symmetries, we will derive this in an alternate manner, where we first promote this global infinitesimal parameter to local ones. And we will still set this first order variation in the action to be 0. And the expression we will have is we will have some constants, we will have some operator multiplied by this partial derivative of the global operator. And intuitively, we can understand your variation is like the derivative of L, right? And so if your infinitesimal parameter is local, then your differential hits that operator, and therefore you will have this derivative of the parameter coming out. So now, if we integrate by parts, because this parameter can be anything as long as it's infinitesimal, this partial derivative hits this j mu, whatever it is, which I say here that it is going to be exactly what we had before. And this is the expression that we need to remember for generalization later. So a charge is then the integral of a Noether's current over the spatial slice. So this is the picture to keep in mind in terms of topologically what is going on, because we will be generalizing this as well in the future, in the rest of the talk. And previously we talked about a classical case, now we have the quantum case, which is the Wall identity, and we talked about correlators in state. And how to understand this, if x and y are not at the same space-time point, then it is exactly the classical case. On the right-hand side, you have 0. But if it's not, then it's modified by this commutator of the fields. Okay, so afterwards, we formulated everything in differential geometry. Your current becomes a one form. We have the Hodge law of the current, and also the continuity equation comes in the form of the exterior derivative of the Hodge law. Now, we also mentioned that this is how we cast the action. Remember, just now we have the current as well as the derivative of the local parameter, and here we have a wedge product. So the charge is then the integral of the current over a d minus 1 dimensional surface, which is our spatial slice. And afterwards, we generalize one form parameters. We generalize the infinitesimal parameters to one forms. This is then the action, and so the action is still a real value, and therefore, if we have an exterior derivative on the right hand side of a one form, this is a two form, and therefore this j itself has to be a two form as well. So that's what we mean of a higher order symmetry, because now this j has two indices. And if we look at the same exterior derivative continuity equation, then what we have is that you have del mu j mu nu equals 0, and remember that j is antisymmetric. Okay, and this is where we finally stopped the previous time. On the left hand side, we have this same continuity equation multiplied by the generalization of the local operator we had. And on the right hand side here, we have something like the delta function as well as the variation in the general generalized field. So we will call this the Wilson loop or Wilson line or line operators. And now let me explain what is a line operator. So in the familiar case of functions, we have if you put in something which if we imagine this is space-time coordinates, you get something else. So that's what we mean by a local operator. So in the example, if you have f equals x squared, then if you put in 1, you get 1. You could put in 2, you get 4, something like that, right? But let's consider something else, which is a circumference function. Now, if I put in a big circle into the circumference function, then we get 2 pi r, where r is a big radius. If I put in something small, then I get a small radius, and I get a small 2 pi r. So that's how I would intuitively understand what we call line operators. It takes in a line, or in this case, a loop, and it spits out something. So this is the expression we had previously, and the rest of the talk will be focusing on trying to understand all the concepts related to this particular equation, which is our generalized word identity. So this is the zero form symmetry, which is our canonical symmetry. We have the fields here, and then we have the direct delta. And now instead of a local operator, we have a line operator. So this line takes in the curve and spits out an operator. Okay? And the right hand side, we are integrating over the entire curve naturally because now we have a curve. So that is our preliminary understanding. Now to better understand this, let us look at one form symmetries in one dimension. In one spatial dimension and one time dimension. So here is a reminder of our continuity equation as well as our generalized word identity. Now, if you put in 0, 0 and you vary this, you get this one. And similarly, if you put in 1, 1 and vary, you get the conservation law. Now we notice that there is something peculiar going on in 1 plus 1 dimension, which is that we do not have a charge operator. And for that, to understand this better, let us revise the charge operator. So first, in the canonical case, we integrate this time component of the conserved current over the spatial slice, right? And we can formulate the same thing in differential geometry. In indices, it's as such, but if you put it in differential geometry language, it's just the integral of the Hodge dual of the current over a d minus 1 dimensional surface. Now this expression shows why we are recasting everything in differential geometry, because it really is much cleaner than having all this mess around if you use indices. And for the one form symmetry case, we have j mu nu instead. And so this dimension drops by 1, we have d minus 2 here. You are integrating over a d minus 2 dimensional manifold. And this is why we don't have a charge operator in 1 plus 1 dimension, because your d is exactly 2, so you're not integrating at all, right? Okay, moving on. So we still have the word identity. Now, even though we do not have a charge operator, we can integrate this word identity over time. So if you have y1 here, then we integrate over here to here, and this encapsulates this direct delta. On the left hand side, then, if you have, let's say, okay, so first we assume a simple case where your C is just a spatial slice, just one dimension here. So if we integrate from y naught plus epsilon to y naught minus epsilon, then this is what we have. On the left hand side, then you will have this commutator because of time ordering. Right? On the right hand side, then we realize that we remove one of these direct deltas because the time integral gives us 1. Okay. Now to recap, on the right hand side, if this line does not pass through x1 because we're integrating over y1, then the right hand side is 0 because the direct derivative just kills this thing. Okay, so that is how we remember there is a classical case for nodus currents, right? But if it does, if this line does pass through, then we will be left with this variation in the line operator. Okay. And the picture, the mental picture we should keep in mind is that I would like to imagine this line, this curve, puncturing this point. This mental picture will generalize very well. That's why we think of it this way. So we have a point here. This x1 is where the j1 is evaluated. I mean, there's going to be two of these things because they're integrating over a certain time interval. So then this x1 is a spatial space-time point, and we imagine that this curve punctures this point. Okay. Now, I mentioned at the start of the talk that this is a topological operator, and here we're going to see why it's a topological operator. So as before, we have x1, and you can imagine because this is actually, there's 2 points. So here is our 2 points. And if we have 2 points, we can think of it as a dimension 0 sphere, right? And so whenever you have a sphere, you can think of what's inside as a ball. So this is a 1-dimension ball, which is just a line, okay? And so here's a topological perspective. We imagine that this line punctures the ball, right? And if it does, then it gives us this link number, which will be just 1. And if it does not, then this gives us 0 on the right hand side, and we recover the classical equivalent of the classical nodus theorem. So why do we say that it's topological? It's because what's important in determining this relation is the link number. If the link number is 0, then the left hand side is just 0. And if the link number is 1, then we have something non-trivial going on. And so you can imagine that we can wiggle this line up and down, right? And this infinite curve can be wrapped around, so to become this. So now you have a circle. And remember that what matters is whether this links, the ball links with the curve. And so we can see why this is topological. We can just move, this curve around, we can move up and down and jiggle it, and your link number does not change as long as you do not pass this point. So this is why we call this a link number. Make sense? Yeah. So this is the topological perspective, and to understand this huge amount of information, we will look at higher dimensions. So now we proceed on to 2 spatial dimensions. So again, we have the reminder of what's going on with the generalized identity. And if you plug in 0, if you let mu vary, if you fix mu, then you have the conservation law. And if you put in specific mu, you will have 2 conservation laws. So now we can define charges because now we see that, remember the charge is defined over a d minus 2 dimensional manifold, and now we have 3 dimensions in total. So we are allowed to define charges, and we will define charges as such. So we will always integrate it. Remember that in the spatial slice of the canonical nodus current, we integrate over the dimensions which are perpendicular to the time slice, to the time direction, right? But now we have 2 directions that we have to be perpendicular, and so if you have J01, you integrate over x2, and we call that the charge corresponding to 1. And you have J02, you integrate over x1 instead, and that we will call this charge corresponding to 2. Now, one important thing to note is that over here, if you select mu to be 0, then this term disappears, and therefore we do not call this a continuity equation. However, what this gives us is that del 1 J10, del 2 J20 here. And if you integrate this expression, what happens is that you will see this Q1 does not depend on x1. Okay, and similarly, Q2 does not depend on X2, and there's something interesting you can note. Now we will march on with the wall identity. So previously we have two continuity equations, and each of them gives us a wall identity. Now we perform the same trick. We will integrate the wall identity to give us the commutation of the charges now with the line operator instead of just now we have J. And so the mental picture we have comes into play again. You have a dimension, we have a parameter which are integrating over this manifold, and we can think of it as the curve puncturing that line. And if it does puncture, then on the right hand side, you will recover this delta, the variation in the line operator. Now again, we can move on to the topological perspective, which is that what matters is in fact this link number, right? So then we can in fact wiggle this thing around. We can close the loop and then shrink it down to we can just shrink the loop. And this means that in fact now we have, instead of 2 points previously, now we have which is S naught, now we will have a 1/5. And so this makes it very obvious why we call this a link number, right? You can see it linking. And we can wiggle both the curve and the S1s around. And to go further, we can even close both curves. Now in 3 dimensions, we still have the same story. So this is our conservation law. Now instead we integrate over 2 dimensions for the charge. And again, we have that the charge does not, let's say Q1 does not depend on X1, Q2 does not depend on X2, and so on. And again, we have the Watt identity. We integrate to get a commutator between the charge and the line operator. And also, we see that we have this C puncturing the plane that we're integrating over. Now, we remember that we are in 3 + 1 dimension, so we can't actually graph the whole space. But let's say we shrink the third spatial dimension. We shrink the dimension parallel to C to a point. And we can see that here we have, in fact, again, a link. So we have this 2-sphere encapsulating this C if we shrink it down to 1 dimension. Now to illustrate why this is important, let us look at something which is 3 + 1 dimensional, which is Maxwell theory. There's some slight nuances because it's a gauge theory, but generally speaking, it illustrates how we use these concepts. So first we have some action. This action is given in terms of F as well as the Hodge dual of F. Now we get our equations of motion, which is the exterior derivative of the Hodge dual of F, as well as the exterior derivative of F, which is the Hodge dual of the Hodge dual. Now, this is the index notation. And then we have again the charges. So you may wonder where are the Wilson loops? And it's actually, it turns out that Wilson loops do not appear in Maxwell theory without matter. To get Wilson loops, we have to add matter. And so once we add matter, which is something local, right? Then we can see that, let's say this is our matter field phi. This is not gauge invariant because if you perform a gauge transformation, then this acquires a phase. However, let's say we define a Wilson loop as such, then this transforms in very nicely the opposite way. So what happens is that Wilson loops appear in this form. If you attach a Wilson line which is half infinite, so it ends on this point x, and you attach this phi to this point, then this object itself, this is gauge invariant. and so we can see why Wilson lines appear in 3 plus 1 theory. Perfect, I'm done. so yeah, a summary of what we covered today, which is we try to understand higher form symmetries better by examining first one form symmetries in n plus 1 dimensions. And of course, this thing generalizes to n form, but here today we just look at the simplest case of a one form symmetry. So thank you.